So, Dr. Kaplan, can we start?
Yeah, sure. So, welcome you all. So, this is our first talk of this year. So, as I mentioned earlier, the last year was very successful. So, this year we are starting with the new topic or this popular talk. So, our speaker is Dr. Suman Deb. So, without further delay, I would request our AIP President, Dr. Sanjay Kumar Singh, to introduce the speaker. Dr. Sanjay, sir.
Yeah. Thank you, Dr. Kaplan. Ladies and gentlemen, distinguished guests and esteemed colleagues, it is an honor to welcome you to this remarkable gathering. I'm Dr. Sanjay, the founder president of Association of Indian Physicists. Today we are privileged to have with us a distinguished speaker, Dr. Suman Deb, sir, Chief Councillor of the Northeast Zone and a research associate in experimental particle physics at CNRS, France. On the behalf of Association of Indian Physicists and the Janardhan Singh Foundation, it is my distinct pleasure to extend a warm and heartily welcome to our esteemed speaker, Dr. Suman Deb, sir. His presence here today enhances the depth and significance of our gathering, bringing forth a wealth of knowledge and experience in the kingdom of experimental particle physics. I would also like to introduce today's speaker, Dr. Suman Deb, sir, whose expertise in experimental particle physics, particularly in the study of quark gluon plasma derived from collide experiment, reflects the pinnacle of scientific dedication. His significant contributions within the HADES collaboration at GSI and the ALICE experiment at CERN's LHC, that is Large Hydrogen Collider, are testaments to his profound commitment to advancing the frontiers of physics. With a PhD from IIT Indore and a master's degree from Tezpur University, Dr. Suman has authored numerous articles and proceedings in esteemed international journals, showcasing his intellectual expertise. Notably, his receipt of Marie S. Curie Scholarship and active roles as an Alice Junior Ambassador and Junior Representative at CERN underscores his leadership and encouragement within the global physics community. Beyond the empire of physics, Dr. Suman Dev's passion for photography adds a unique dimensions to his multifaceted persona. His commitment to serving the community and advancing the field resonates deeply, making him an exemplary figure in the world of physics. Welcome, Dr. Suman Dev, sir. Your presence truly elevates the importance of our event, and we look forward to an enlightening and collaborative discourse. Thank you once again to all of you. Over to you, Dr. Captain.
Thank you, Dr. Sanjay, for wonderful introduction. And I thank Dr. Sumante to agree to present, to give this talk on our platform. So now, without further delay, I will request Dr. Suman, please start.
Thank you so much. First of all, thank you so much, Dr. Sanjay, for giving such a warm introduction to me, and I am really privileged to speak in this particular forum. So maybe I'll start with sharing. Okay, please let me know if you can see my slides.
Yeah, you are invisible to us.
Okay, and my voice is okay?
Yeah, it is fine.
Okay, fine, perfect. Okay, so thank you everyone for coming here today. So I have prepared a slide, mostly keeping in mind our undergrad and grad students. But of course, there are some higher advanced topics are also there related to my research. That is at the end of the talk. Okay, so my talk is related to what are some of the stepping stone or some of the moments that we have come across during the evolution of our physics study. and how those moments have shaped in making our future better. So, if I see that broadly, our physics world is have three more realms. So it can go from a quantum world to a cosmic world to classical world, covering a length of almost 10 to the minus 25 meter to 10 to the 25 meter. And for our undergrad students, so 10 to the minus 25 meter, you can realize it by thinking that the dimension of our diameter of our hair follicle is about micrometer, which is 10th leg, one of 10th leg of a meter. So it's that small dimension is quantum world. And as we make our journey through quantum world, classical world, and cosmic world, we come across, we think of many questions. So those questions are many, and not all questions are answered. But in this talk, I inspired to deliver a message that the questions are to be asked, and not necessarily we will answer those questions instantaneously, but the pursuit of those questions is what matters. So that is my intention of today's talk. So some of the questions that we come across are like, what is our understanding of this universe where we live? Then followed by, there's lots of talk about quantum world, quantum mechanics, how those quantum mechanics world is defining our intuition. There is also talked about space-time fabric, very famous. So what information we are actually getting from space-time fabric, and why we have actually come up with the quantum space-time fabric. Then the important question, which is very much close to my field, is what is the constituents which meet the fundamental state of the matter? Followed by, can we unify the forces of the nature? So as we are move, if I focus more on my research area, that we have some fundamental forces in nature, and we inspired to see if we can combine all the forces. So these are the some questions. Of course, this is not only, there are many more, but let's try to see in this today's talk if we can answer this question and can have some interesting discussion. Okay, so yeah, so let's welcome to this talk, and here we attempt to understand some of these challenging questions. Okay, so the first question, which is age-old question, is the understanding of our universe. So
Excuse
universe
me,
is a
sir.
very, yes,
Hello,
please.
sir. We have not seen your slides.
Actually, it is visible. It is visible here. Anyone else has this problem?
Yeah, we have not seen your slides, sir.
No, we have
Presentation.
maybe
Have you
might
saved
have
the
internet
presentation?
problem.
Okay. So we suggest you to please. It is visible to all. So you may try
Yes,
rejoining,
please.
or yeah, there is some issue.
No, there is no issue. There is a network from the participants. Those who are facing
Yeah.
slide problem, there is a network problem.
At their end, not
Yes.
our end. Yeah. So yeah, please, Dr. Suman Deb,
Please rejoin. So please
Okay.
rejoin. Yeah, you can proceed
Okay.
further.
Okay, that's settled. Okay, so yeah, so I was talking about, so let's try to invoke those game-changing moments. So the very age-old question that we have is the understanding of our universe, how our universe is created, where from we come, and everything. So if we trace back to very old, back in centuries, then it was understand, it was believed basically that Earth is the center of the universe and everything around is revolving around it. And why make such claim? So their claim could be various reasons why they are making such claim. As, for example, we can understand that they see that sun rises and it covers throughout the day and then it sets. So it looks like we are sitting and everything is moving. So basically, they come up with this idea because of their intuition. They see around themselves and they make the assumption. But this assumption was understand, or it is people have assumed it for a very long time that okay, this is the real truth, this is how it's working, and this is how the universe is designed. But in between, there comes a philosopher called Nicholas Copernicus, who have dared to ask a provoking question that is it really the Earth is at the center, or it is the sun which is the center and everything around revolves around it. The question comes why someone is challenging an age-old concept that Earth is at the center. So it's because of various reasons again. I have just put one of such his understanding. One of his understanding is the uneven planetary speed. So Copernicus, he have observed sky for a long time, and he recorded the data, let's say in terms of speed. And what he found is that the speed of the planet around the Earth is not same. It's moving with a different speed. So if we assume that is true, then Earth cannot be at the center. Because if Earth is the center, then everything else around we see is moving with the same speed. But Copernicus observed that not everything is moving with the same speed. So that is one of his moment where he understands this concept that Earth is at the center may not be true. There are many other observations. For example, he made the calculation of the previous calculation he challenged done by the previous philosopher, and he observed that if we keep sun at the center of the universe, then all the mathematical consistency observation can be explained. So this is the what Copernicus have observed. Now, what is the impact of such claim, and what is the impact of such revelation? So the impact is that the first very important impact is that we understand that we have to ask questions, and it is not necessarily what you are observing is true, but you have to make everything consistent with respect to surroundings. So this is a moment where we see the first game-changing moment in the physics, where someone has challenged the age-old concept and given a new concept where sun is at the center of the universe. And with this concept, we could explain most of the thing around us. Okay. Now this is a very simple understanding. Now next, I would like to look into another important question: is how does the quantum world define our intuition? So to understand this one, I have to see what is the difference between the classical world and quantum world. So classical world is the world that we live in, and quantum world is the world inside the atom. So if I see this two picture, on the left hand side is the classical world. So in classical world, we can work with intuition. So you see in the picture, a tiger is chasing a deer. So if you want, you can here actually apply classical mechanics, because your intuition will work. You can say after 5 minutes where the deer will go, and tiger can exactly reach to that point. So with intuition, we can work in the classical world. Exactly, you can calculate if you know what is the position of a deer at certain time. You can exactly say where would be deer at after certain amount of time, and this is done by classical world. But when we switch to quantum world, we observe that this intuition of ours fails, and we cannot apply anymore this concept that knowing position at some point, you can predict what will be the position at next point by simple classical formulation. So that's where our intuition from the classical world fields, and it lead to develop a new world called quantum world, which develop a new physics called quantum physics, and this this quantum physics have changed many things. So I would like to talk about some of those quantum physics phenomena which challenges our intuition, that is classical mechanics physics, and how they emerge. So such one of such those puzzling phenomena is the famous wave particle duality. So our understanding is, our intuition says that there is a particle, there is a wave, and these two are mutually exclusive events. They do not match, they are separate quantity, and they to be treated separately. But when we jump into quantum world, we come across this phenomenon where the concept of wave and particle vanishes, and a entity can behave both like a wave and a particle. So which give rise to a phenomenon of wave particle duality. So what does it challenge us? It really challenges our intuition that world is actually made up of wave and particle separately. And here we have to challenge ourselves, and we have to come with a new intuition that we can treat both of wave and particle together. Okay. So we have similarly many such puzzles. If we come across many puzzles we have, but I want to take very interesting one called the quantum entanglement. So this is again a quantum phenomena which is totally different from what we really observe in our everyday life. So what is quantum entanglement? So quantum entanglement says that two bodies which are not connected anyhow, they can behave together. For example, a person in India, a person in US, they are separate from each other. But if a person in US eat a food, then the person in India will eat a food at the same time. We say that they are entangled, quantum entangled. But if I see my classical world, should not work. It should not happen. But this says that the rule of the game is very different when we go to the quantum world. And this again is a game-changing moment for us, because we realize that when we go to a quantum world, the thing is different from what we have learned in our classical world. Okay, so but with this understanding that okay, the quantum world is different and we have now certain rules, how does it help us? So it has helped us in many ways. For as you can see, understanding of quantum world have really revolutionized our electronic system industry. We have now laser, we have transistor, FET, MOSFET, which are actually the results of the quantum world. And also, if I come to my field, then quantum mechanics of understanding of quantum has actually helped us to identify new particles. Besides the known particles, we could also identify new particles with the understanding of quantum world. So this is again a game-changing moment where we jump from classical mechanics to quantum mechanics, and we don't apply the same rule as classical mechanics, but we develop a new rule in quantum mechanics, and we can use those rules to make our life better by creating new devices like laser and transistors and so forth. Okay, so yeah. So then I have now I'll jump to topic which is very much interest to me, is how to study the creation of universe. If this universe has created, so there has to be a point where it has created, and and it has must pass through different phases during its evolution and reach to the present day. So if we want to study, we want to trace back, how can we do that? Okay, so here is a conjecture picture how could have universe been created. We don't know for sure if this is the truth, but we can make a theory. So universe must have created from Big Bang, which is actually the expansion of a point. That point has expanded. It passes through the different phases, as you can see here, and it reaches to a stage after 13.7 billion years, which is the present universe. So, can we find out if this is possible? Is it really how the universe was created? If we can do that, then we could understand how our universe is created. How we'll do that? So, I have a picture of this is an artistic picture. This is a much more scientific picture of the previous step. So as you can see here, let's say we assume that the universe is created by Big Bang. Again, we don't know if this is the only true, but if we assume that the universe is created from Big Bang, then coming to the present phase, it's not happened straight away. As you can see, it passes through different phases. It starts with inflation, then there is a production of quark, which is the smallest particle. Then those quarks combine to form proton neutrons. Then those proton neutrons combine to make molecules. Then those molecules combine. Then they form planet, stars, and so on and so forth. We have a present universe. Now, if I want to know that this is really the evolution of the universe, how will I proceed with that? So one of such way to know if universe is created, how we have a collider. We do a collider experiment. So here in this picture, this is a screenshot of Large Hadron Collider at LHC. So you can see it is a circular ring. So we make two particles collide. We make two, as you can see, there are two rings. So in both the rings, particles are accelerated in the opposite direction. And at the connecting point, as you can see, here is a connecting point called LHCb. Here is a connecting point called Atlas. Here is a connecting point called Alice. Here is a connecting point called Suman. At this connecting point, those particles are made to collide. Now, when they collide, we know there will be transfer of momentum, transfer of kinetic energy, and those energy will create very high temperature. And those temperature, if it happens to be this temperature, then you can actually go in this region, right? So we make sure that when we make the collision of the particle, it produces enough temperature such that it reaches this point. So as you can see, if you want to reach this point, the temperature is almost 10 to the power 15 Kelvin. So we make sure that when we make such collision, we produce that much temperature so that we can reach at this position in universe evolution. Now, if that happens, then we will see that is it really evolving the way we expected. If it's evolved, then this theory that universe is created like this would be confirmed. Out of all these detectors, I work on a particular detector called Alice. So this is a Alice looks like. So this is a Alice detector. So as you can see, there is a beam line. This line is passing through this detector. This line is actually this two lines where the particles are made to collide. And you can understand this detector as a big photograph. It's just a photograph, photo camera. Which what happens is that when two particles collide, it produces lots of small particles. Those small particles are collected by this different detector You can see different color means it's a different detector. So those detectors act like a photo camera of the collision when this happens. Okay, so that you can see if really the evolution is like this or not. All right. So okay, so how we proceed like this? So we assume now once this collision happens, how this from this point to this point, what is happening from the point where it's collide to the point it is detected in the detector, what is happening? So there are many theory about it, how this would happen, but we have very much accepted model how it works. So this is the picture of that model. So it says that here we have two particles which are colliding. Once they collide, they produce enough temperature, enough energy to create a state shown by this purple color called quark gluon plasma phase. Now, what is quark gluon plasma phase? So I'll go back. So this is the quark gluon plasma phase. So you can see that what happens in quark gluon plasma phase, you have only, as you can see here, is only quark and gluon. It's a state which have no other particle like proton, neutron, and so on and so forth. But it has only two particles, quark and gluon. And quark and gluon are the building blocks of particle like hadrons. So in this phase, we assume that quark gluon plasma is created. Then as it moves toward the detector, this is the place where the detector is, its temperature reduces. Remind you, here the collision happened, the temperature is very high, so we have quark gluon plasma. Now as it approaches towards the detector, its temperature decreases, and at this point, its temperature decreases to such an extent that no more becomes quark and gluon, but it becomes now a particles. For example, proton, pi, and k1. Those particles become. Then it passes to another phase where there will be no new particle will form, and finally the particle will be detected in the detector. Now, by studying this particle in the detector by some smart techniques, we can know that is it really true that
Yeah. Sorry to interrupt you. Is it a network issue from someone's side?
Your voice is not.
Yes, I think.
Yeah, your voice is not coming.
Yeah, Suman sir, recheck your
maybe
please.
issue.
Still your sound is not. Yeah, okay. Captain, he will
Yeah.
rejoin.
Okay.
Yeah, in the meantime, you can announce something about our website and social media platform to the audience.
Yeah, announcement links are there. So if anyone has any questions, they can post their questions here. And he's reconnected. Yeah.
is my voice audible?
Yeah, sorry, yeah, completely fine.
Okay.
Audible,
Okay, I
sir.
don't know.
No issues.
Okay, is slides are visible?
Yes, yes, complete.
Yes, yes.
Okay, okay, sure, sure. Okay, please let me know in between if there's some issue with the audio, then I will stop.
Yes.
Okay, so I was saying that the job of a particle physicist is to study, analyze these particles which are created in the detector, and confirm whether this kind of theory, where people, theories say that this happens, is it really true or not. So what we do, we collide two particles. So here I want to show that the collision of the particle is not random. We just don't collide any particle. So for example, if you collide lead kind of particle, which is a very heavy ion. Why I'm saying it's heavy ion? Because lead has got lead nuclide has got lots of protons, and so it's a heavy ion. And if we collide such particles, then this is how the detector look like. So and to show that this is the region I'm talking about. So how this region look like? This region look like this. So here you see many colors: green, purple, red, and everything. All this color is the path of a particle which have come out after the collision. So you can see that when two lead particles collide, lots of other particles appear in the collider. Now, to understand this, if I compare this with a collision of now proton and lead, then you see the picture has now reduced. Now, number of line or the density of this line have now reduced. Now, to confirm this event, we'll now collide even more smaller particles, only proton-proton. So, if I only collide proton-proton, now the density is got even more smaller. Okay, so you can see this comparison. So if we collide lead-lead, we see lots of particles are produced after collision. But if we collide proton-proton, then very less particles are produced in this in the collision. So the difference is this. So theory says that if we have a proton-proton collision, then you don't see lots of particles, and this kind of scenario is not true. This may not be there. This type of scenario is true only when you have a large number of particle producing, that is by lead-lead kind of system. So the aim is that if you can prove by analyzing this data that this theory is correct, which means quark-gluon plasma phase is correct, and if quark-gluon plasma phase is correct, that means this phase is correct. That means our universe has actually evolved through Big Bang. So that is what the job of an experimental particle physics. So I'll proceed with some of the results in this direction. Okay. So this is what I want to say, that if we can prove that these phases exist in the experiment, in the collider experiment, we can actually say that phase is available. This phase is there in the universe, evolution of the universe, and that really confirm that universe is actually created from Big Bang. So that's the main primary objective of an experimental particle physics. Okay, so in this regard, we have done many investigation, and one of such investigation is called strangeness enhancement. So strangeness enhancement says, before I talk about this nice plot, I will just say that the strangeness enhancement says that there will be large number of strange quark production. So what is the problem? So problem is this: when you collide two protons, protons have only up quark and down quark. There is no strange quark. But after collision, strange quark produce, and hence that says that QGB kind of phase is there. Quark-gluon plasma phase is there. So now you can see here in this plot. Here in this plot, we have a ratio of two particles. So in the numerator, we have a cascade particle, and in the denominator, we have a pion. So what happens is that pion is made up of only no strange quark is there in pion, but in the cascade particle, there is a strange quark. And we see that this plot is increasing as a function of multiplicity, but it is increasing. So this increasing trend says that there is a strangeness enhancement which says that QGB phase is there, which confirms that Big Bang kind of scenario could be true. But of course, only from one measurement we cannot conclude that everything is good. So we have other measurements also. So we have a measurement of something called nuclear modification factor. So what's nuclear modification factor is about? So this nuclear modification factor is about it's about in the numerator. Okay, let me only talk about the stuff which is important. So in the numerator, it looks very complicated, but it's simply a number of particles. Particle a particle which is producing heavy ion, and in the denominator we have a particle which is produced in the p deposition. So just to remind you, just to show you that, so you see that when you collide heavy ion like that, you have a large number of particles produced, and when you collide proton-proton, very less number of particles produced. Now what we are doing here, we are taking ratio of a specific particle in heavy ion and small PP system, and we are scaling this small system such that numerator and denominator is same. Now, if this ratio turns out to be less than 1, it means that some of the particle is lost in numerator, right? Because it's less than 1 means it's lost, some of the particle is lost. This loss of particle is also an indication that there could be a QGB kind of bridge. So people have worked on this particular respect, and and they come up with this result. So in this result, you can see it is a this factor RRA, and we observe that this value is less than 1. So clearly shows that the numerator is less. That means the number of particles in heavy ion has vanished. So which indicates that QGB kind of medium could be there in evolution of the universe. Okay, so all this is done with the assumption that proton-proton system, there is no chance of QGB formation. Why so? Because if you can see in proton-proton, the final state particle is very less, the density is very less, the density is not enough to produce QGB kind of scenario, but in heavy ion, the density is very large, it can produce QGB kind of scenario. So people have worked with this assumption for a long time that proton has no such QGB kind of scenario. But this is exactly the moment of Copernicus and the earlier philosopher, where Earth is assumed to be at the center, and then Copernicus come up and he talked about sun. So this is exactly the same moment where people assume that in PP there would be no QGB kind of scenario. But recently there is a game-changing moment, as I call it. So what people have done, they have calculated the similar ratio, the strangeness enhancement ratio, where in the numerator strange particle is plotted and denominator no strange particle is plotted. As I say, if there is a QGP, then you see that more strange particle will produce, and this is the result of this ratio in proton-proton system, that is small system, and we see that there is a rising trend. So this rising trend tells that the assumption that proton-proton system will not have QGP may not be true. It may have QGP kind of system. But this is a very latest, very latest game-changing moment, and people are working tirelessly to confirm that is it really true or not. And I think this is what we are all working on. Okay, so I have some takeaways from this part of the work. Okay, so what we see from all these examples, right from the Copernicus to quantum world to this experimental particle physics, we see that the game-changing moment always make a paradigm shift. It really challenges the old concept and come up with a concept which is almost 180 degrees from what is originally believed. So this milestones really tells us that we have to always be curious about stuff and not take anything for granted unless it is backed by all scientific pointers. And we should always try to look for more insight in any given topic. Okay, so I think this is where I'll stop now. And yes, thank you so much for your attention, and maybe I'm happy to discuss on everything. Thank you. Thank you so much.
Good afternoon, sir. May I ask some questions?
Yes,
Yeah,
please.
sure. Yes, sure.
Sir, I just wanted to ask, sir, you told in your slide that proton is a point object. But sir, how can it be a point object? I mean, we know that it is made up of quark particle.
Yes, you're right. That is what actually is assumed that when I say point object, I don't mean that its volume is zero. Of course, proton is a finite radius, so if something is a finite radius, so it cannot be a point particle. So what I mean to say is that with respect to heavy ion like lead, we assume that proton-proton system have no contribution to formation of quark-gluon plasma phase. So in that aspect, we say it is a point particle, but not literally it's a point particle. So you are right.
Oh, thank you, sir. Sir, one more question, sir. Sir, I just wanted to ask, sir, we basically read in electromagnetism or in nuclear physics and particle physics also that charge is quantized in units of electronic charge. I wanted to ask what will happen if charge is not, because sir, in most of the books it is not mentioned why is charge quantized. We usually in books it is mentioned that charge is only quantized. I wanted to ask what is the reason, what will happen, and how physics will change if charge will not remain quantized.
Well, I think I will give you a spoiler now. So charge, if you see the charge of a quark, charge of a quark is not quantized. It's a fractional value. Okay, so the point that the charge of a proton, for example, you say charge of a proton is quantized, like it's a integer 1, 2, 3, 4 like that, right?
Yes,
But
sir. Yes, sir.
if I take a proton now, then inside the proton we have the quarks, 3 quarks, and those 3 quarks have charge. Now you have to make sure that charge of those 3 quarks are such that the final charge of the proton is quantized, +1, right? +1. Okay, so you choose charge in such a way. So the charge of those quarks now turns out to be 2 by 3, 1 by 3, like that. Now, okay, so this concept that it has to be always in is available.
But sir, the thing is, sir, but the thing is, what will happen if it not remain quantized? I mean, see, sir, if proton is made up of up down quark, then it is explainable. Sir, how we can relate this to electrons in case of electrons? Because electron is a mathematical particle.
So this is a okay. This is a very broader question, but I would say it's kind of a convenience, right? I mean, why it has to be 1? Why not charge of an electron is 2? I think it's just a convenience. It's a matter of convenience. But what will happen if the charge of electron is fractional? Okay, if charge of a quark is fractional, then this also tells that the electron is not a fundamental elementary particle, right? It could be composed of even more further particles. So there could be many implications if charge of electron or any particle is fractional. So one I can think of right now is this also tells that the given particle is made up. It's not elementary, but it could be made up of even more other particles. But yeah, you know what it was.
Yeah,
You,
I would like to add something to your answer.
please.
So yeah, so I guess this quantity, this charge number is just a convenience, as Dr. Suman has
Yes.
mentioned. So like what it is in order of h cross, you can understand it this way. Okay, so in quantum domain, we say that it is -1 or +1. This is for our convenience. But as of now, there is no minus or plus thing there, right? So we say that, okay, so electron is like elementary particles. We have defined the charge 1 to this. Then according to that, proton has charge +1. So with this convenience, if proton has 3 cos, all the charge, total sum of the all the charges, the fractional charges should be 1. So that's how the charge assigned to the quarks is in fractional form. So that is the convenience from coming from
Yes,
hadron.
Thank you.
I-
Thank you very much.
I think we can say it safely that the charges that is mentioned is it's a convenience. Convenience.
Yeah. So we have other questions. So I think I would take this question first. So what about the charge quantization in the tetra quark and penta quark? Suman, you would like to answer this
Yes.
question?
What's the question?
What is the charge quantization in tetra quark and penta quark?
Okay. What it will be? I think it's the same question. I mean, if you take a penta quark, then it will again be. It will be of some integral value, right? It will be some integral value. So if I see penta quark, it is got 5 quarks. So that means combination of baryon and meson. So both is integrals, so one sum is integral. So again, it's a convenience. It's a convenience.
Actually, penta quark charge is only 1 because it is a combination of proton and depth size. So depth size is the boundary state of CC bar. It is charge 0.
Which is meson.
Okay.
Which is meson.
And the proton has +1 charge. Okay, so like penta quark is found recently, let us see, it has +1 charge. And
Penta quark is baryon and meson, and tetra quark you can take it as a 2 meson.
2 meson, yeah, simply.
So it's fine. So it will be integral. But I think that is understood. But I think again the point is again that is a convenience. Convenience.
Right.
How you define this initial charge.
So we have few other questions.
Let's talk about
So okay, Amrut asks, can you explain the process hadronization? There you said about the pions are pion mesons. That is,
explain the process of hadronization, I think, right? Explain
Yeah,
the process of hadronization. Yes, I think that's a question. Okay, so maybe I'll show you from a picture. Okay, so okay, so what happens here? So in this phase, you have only quark and gluon, and as it proceeds toward the detector, its temperature decreases. And as this temperature decreases, what will happen? It will start to, quark will start to, there is a property of a quark, the very special, not necessarily properties of quark. So quark and gluon are studied by a theory called strong interaction. And what is the two important property of strong interaction is that the quark will have asymptotic freedom and quark confinement. So what is quark confinement? Quark confinement is that you will never able to see a isolated quark exist. All these quarks will combine. Now, why it is so? Because let's suppose we have a 2 quarks and we try to expand, we try to separate them. When we try to separate them, we need to apply energy to separate them. But that energy will be always enough to create another quark. So that means you will never be able to have a single quark in isolated form. And so what happens is that as the quark approaches toward the detector, its temperature decreases, and as its temperature decreases, the quark confinement property will come into picture. So all the quark will no more stay in the isolated phase, but they will combine. And the rate at which they combine, it depends upon the cross section. So if suppose it is supposed to form a pion, then it will depends upon the cross section. The two quark will combine and it will form a pion. And when this happens, we say that the pion got hadronized, and we say that the entire process is hadronization. And this happens at this stage. At this stage, this happens. After this, there will be no more hadronization. As you can see, here it is written hadron, let's say, hadron. So it's only the hadron in this case. There is no more quark. So yeah, and those quarks move, and when they are very much far from each other, they are detected. You want to add something, Dr. Captain?
Yeah, I think it's fine. So, yeah, you have completed.
Actually, because there is no response back from the one who asked the question, so it's really understandable.
There is said about pions or pions. Are pions mesons? Yes, pions are mesons. So, quark and quark combination is the form of mesons.
Sir, may I ask one more question, please?
Yeah.
Sir, Suman sir, you told that within the QGP phase to hadron gas phase, there is something called as viscous hydrodynamics. Is this viscous nature is same as that we observe in our fluids?
Observe in our?
I mean, the viscosity that we have discussed here is same as that we observe in fluid dynamics?
Fluid dynamics.
Yes, exactly.
Yeah.
The hydrodynamics, this is the exact one. There's no very advanced stuff. It's all basic. The basic is what you are saying, viscosity is exactly that. So what happens is that, so you must know why, if maybe, I don't know, the question that you asked, if you got the answer or not, but the question, maybe you can ask why hydrodynamics is mentioned here. What is the purpose of this hydrodynamics? So if you ask that question, I think it's a different answer.
So I think here about the viscosity. So yeah, so QGP is a viscous force. There is viscosity in the hydrodynamics that is there, but it is the minimum viscosity present in the nature. So that is there. So it is around natural unit. So we say 0.2 or something natural unit, I guess. 0.2, 0.8, yeah, something 0.08. Yeah. So there is another question. Hers has asked, how is the working of LC different from a fusion reaction?
From fusion?
From a fission.
From fission? Okay. The fission, the sun one, right? The breaking of helium. Yes. Yeah. Okay. So maybe to answer this question, I will show I'll show you two pictures, LHC working and fission one, and then maybe you can make your mind on that. So at LHC, your aim is to create energy. What energy? This much energy. 10 to the power, almost 12 Kelvin of energy you want to produce. That is it. Why you want to create that energy? Because if you create that energy, when I say energy in layman terms, I mean temperature. Okay, that much temperature I want to create. If I create that much temperature, I will be in this region. In this region, I have a quark-gluon plasma. So if I can create this one and observe how it is evolving, I can make a conclusion whether this theory is right or wrong. So aim of LHC, create this much temperature. Now, how we create that much temperature? That's the next question. So to create that temperature, you make two particle collide. So you can see in this ring, there are two rings. And so what happens? Suppose in this ring, you make one particle go, in other ring, you make other particle accelerate, and they are in the opposite direction. And you can see there is a connecting point. So at this connecting point, those two particles collide. Now you know from I think class 11 physics that when two particle collision of two particles, you can calculate exactly what is the kinetic energy produced, right? If it's an inelastic collision, then you know exactly what will be the kinetic energy produced. So if you can produce kinetic energy now, then you can reach to this temperature and you can study the universe. So that is LHC's job. This is the job of LHC, and LHC does that. And I think in fission reaction, you are more interested in producing you want to you want to do a reaction where you combine two hydrogen to produce helium, and that corresponding energy will produce. And I think in the fission process, you don't have to make two hydrogen collide, right? Only in the vicinity, I think if it's kept in the vicinity, then it can produce enough energy. I'm not exactly sure. Maybe I think Dr. Captain can want to say something about it.
Yeah, fission is like breaking of like heavy ion. So here we are smashing two particles. So smashing will, so there is no difference in energy. So here energy and mass is same. In fission we have one ion at rest and other is being bombarded, like neutron is being bombarded on the heavy ion of any radioactive element, right? So that is the case there. But here we are smashing two ultra elastic particles. So both the particles are very high speed. They are near to C. So like they are, so at we reach to the speed of light, their particles are getting heavier. So like 1 GeV proton get to 7 TeV or 13 TeV. So the particles which are producing, they are only quantum of energy. So there is no difference. So it is right. I think we have covered all. Yeah.
Also, just I would like to mention, I think the energy that is created in the collision of two particles in NH3, that energy is very high compared to the energy that is created in sun. So if the fission reaction is happening in sun, whatever energy is produced, right, that energy is not enough to create quasar. So as you can see, in this phase, the temperature is 12 Kelvin, and I think the core of a sun is only 6,000 Kelvin. So even if the fission reaction you do, and you, I think this is what I meant. If you do fission reaction and you try to study quasar, you will not able to do, because you will not produce enough energy.
Actually, so like fission, the energy is not that much to create the heavy particles like gypsum or any heavy particles. So they are only creating the photons. So like Suman got confused. So he has asked about the fission, not fusion. So you are talking about fusion, I think. So you will not have heard me properly. So like in fission, you get the photons only. So you don't have that much energy to create heavier particles. But at LSC, the energy is that much high, so you can create a very heavy particle, or the fundamental particles which give the mass to all the particles. It's called Higgs boson. According to the Einstein model, that is also been discovered at LSC. So that is possible. That is only possible if you have energy too much high, like in TeV range. Then only you can produce such a particle.
Because this theory says itself that you need 10 to 12 Kelvin.
So I hope there might be also in the difference of the cross section, scattering cross sections of plays a very important role in both the collision. As Suman sir and the Captain sir will also explain about it. So just adding to them, in case of the nuclear fission, the bombarding, what we call is a slow, thermally slow neutrons is going to bombard on the heavy nucleus. So here plays what happens is that the cross sections of the nuclear fission is little bit larger as compared to the cross sections of the collisions in case of the two the part LCH. So here what I would like to say is that one is the slow neutrons, and here the speed or the velocity of the two colliding particles is very high, leads to the production of a very large amount of energy. This is one factor. And secondly, as I have said, it's depend on the cross sections, because if the cross sections is very small, in case of the in the nuclear fission, it will not occur any nuclear fission. So the cross sections must be little bit, comparable to the fusion of the neutrons and the nucleus. Thank you.
Yeah. Thank you. So, like we have another question. Dharmendra Singh has asked, what progress has been to combine all forces in one formula? I read in magazine that the speed of particle can be more than light speed, while according to Einstein theory, it cannot be.
Okay. Why he said okay? So that's not true, right? You can have a particle with speed more than c, but that depends upon which space-time zone you are in. right? There is a particle called cyclone, which cannot speed more than c. But this particle is not detected, and there is no way to detect that particle. But I think what you understand, what progress has been made in combining forces.
What
Right.
forces has been, what progress has been to combine all the forces in one formula?
Okay, so okay, that is a very question. I think progress is, I think, till now we have reached to a point where Professor can of course correct me. I think we have reached to a point where we have a four forces in nature: gravitational, electromagnetic, weak interaction, strong interaction. And right now we could manage to combine uh, electromagnetic force and weak force. Therefore, electroweak force. I am not sure. Okay, gravity is excluded. Gravity is not included yet. And yes, that is a progress as of now. I think we have only combined electromagnetic and weak force, and rest of the other forces are not combined yet.
Yeah.
Yeah.
So yeah, so I think Suman's talk was mainly focused on that aspect also. So like electromagnetic and weak force has been combined, as Dr. Suman has mentioned, but we are struggling to combine the strong interaction. So that is why we are trying to understand the real nature of the strong interaction. So right at present universe is made of baryons or mesons. So what is the strong interaction would have been in when it was born? So that's why we are looking to the early universe when Big Bang, all the matter was in deconfined phase. So at that phase, that's why we are probing the quark-gluon plasma. So if we know the true nature, then we may find a way to combine at least strong force to the electromagnetic and weak force. So that is SU3 standard model. So standard model combines SU3, that is strong interaction term. So this is a specific group SU3 cross SU2 and U1. So this is the theory for combining three forces. Gravity is like very far from here right now. So at present, we are trying to combine three forces. We will discuss about the gravity in future, maybe after 50 years or 100 years, we don't know. So presently, we are struggling with to combine these forces, three forces together. Yeah.
Strong.
The next
So
question,
can you strong interaction?
Yeah, yes. So other question is, can you elaborate the concept of strangeness enhancement a little bit more?
Yes. So I will try to go in more. Okay. So what I want to say by strange enhancement is, but the name is strange enhancement. That means production of more strange particles. Now, when we collide two particles, as you can see here, when we collide two particles, these are two protons, let's say, two protons. So proton is made up of up quark, down quark. So there is no strange quark. So you are colliding two protons which are made up of up and down quark. But question is how strange quark will produce them. So to understand that, we have to understand what is the mass of a strange quark. So mass of a strange quark in its bare form is very small. And if you create a KGP-like phase, as we say, KGP-like phase, here it is possible to produce all sort of quark, all flavors of quark. So it can produce up quark, down quark, strange quark, everything can produce in this phase. As this phase is completely made up of quark and gluon. So if this phase exists and this phase produced in the collision of two particles, that means strange quark will produce here. And if a strange quark will produce here, in the final state, you will see particles made up of strange quark mode. You should see particles which are made up of strange quark mode. That is called strangeness enhancement. That means particle with strange quark will be more. And that is possible if we have a TGV kind of phase produced in the collision. So yes, that's what I'm saying.
So Akshita had asked, before the Big Bang, the universe is in the 0 dimension.
Dimension means which dimension? Time dimension is okay.
I don't.
Space-time.
So
Spatial
I think
dimension.
she's talking about spatial dimension, space and time. So like we consider
Yes.
time from also.
Yes. So we have to decay theory assumes that the point at which the expansion starts is 0, 0 point. So space dimension is 0, time dimension is 0, and everything started from that point. Yes, and that's what the decay theory assumption is.
So, does anyone has any other questions? Iska is there. Iska Chakravarti, she is our youngest participant.
Excuse me, sir. One thing I just wanted to ask, sir. You told about weak force, strong force. Sir, we read that weak force only participates in beta decay. Sir, is there any other evidence of weak force? I mean, weak force participates in some other phenomena also. Is there any evidence?
Where you
Or
see
is
weak force?
it?
Well, right now I cannot think of any example.
Yes, yeah. I think someone knows the answer. Decay of kaons, K mesons, they decay.
Yes,
Okay.
decay of
Thank you, sir.
So yeah, Iska, she is our
decay of
youngest
all strange
participant.
particles to weak decay, right? Decay of
Yeah,
all strange particles to weak decay.
yeah. So Suman, she is our youngest participant. She's class 9th. I think she was on to high school now. So
Yes,
yeah,
Yeah,
sir.
do you have any questions?
Sir, I don't really have a question right now, but I would really like to say that I am really amazed by what sir told today. You know, I like in my spare time, what I really do is study a little bit about the fundamental particles. And today it is one of my kind of dream come true things, you know. But I would like to ask, you know, it's a very general question. If we are at the very base made up of quantum mechanical objects, if quantum mechanics is really what it makes us, then why can't we find a relation in the classical world? Why is it not we can't I'm throwing a ball here and it is going there? Why can't we observe quantum entanglement in real world? Why is it that we do have to go dive deep to the small scales? What is the relation with this scale and the physics? Can really scale affect physics? That is one of my questions.
this is a very good question actually, and this is what we have to understand. So you see that it's like you are playing a game, okay? And to play a game, you must know what is the rule of that game. For example, you want to play chess, then you must know what are the rule of playing chess. Now
Yes.
you have now learned what is the rule to play chess. Now
Hmm.
I'll give you now a carom board. Can you apply the same rule to carom board and play carom board?
Not really.
Carom?
Yeah.
You cannot, right? So
Hmm.
you have to discover new law to
Hmm.
play carom board. So it is exactly the same. So when we are in a classical world, we we find out a rule in physics, we call it law, to understand the universe around us. But when we go down scale, that is, for example, the everyday life is meter. You can see how much is 1 centimeter. But if we go little more down, then we assume that the rule should be the same. But it's a case again, it's a carom board now. It's a different rule. So we see that this dimension, the rule of what we learn in classical world doesn't apply. You make a new rule to understand that one. Yes, so that would I'd say that it's all about the dimension. At what dimension you are playing the game. If we change that by dimension, let me say length. I mean to say the
Hmm.
length. The length. It's all about the length. You change the length, the game of the rule of the game changes. And this is what the observation we have so far. We see that low, if you go, it's a different rule. Normal world is a different rule. But if you go to space, it's a different rule.
Yes, sir.
And yes, yes,
Yes,
that's what
sir.
it is. So,
Thank you, sir.
Because I think
Okay.
Katusha want to add something to this. Area.
Yeah, you gave a very good answer actually. So like she's a high school student. So when she would learn in higher classes, so she would learn that from classical and quantum, they merge together in one point called quantum field theory. So like he's working on. So so classical theory, if you add a little stick term there, so then it will go to classical field theory. And in quantum mechanics also go to quantum field theory. So you can come quantum field theory through quantum mechanics, and you can come through quantum field theory through classical field theory also. So this is the point when these two theories merges together. Okay, so like at different scale, physics just different, but at the origin, or everything is same, right? So in quantum field theory, it is same everything. When you change the scale, you will get two branches. That is called classical physics, and other is quantum physics. So there
But
is
sir,
no
where
basic.
does string theory stand here?
String theory
Okay.
is a theory. Yeah, someone can answer here.
Okay. So I'll say this again to understand the rules of the game in quantum world.
Hmm.
It is one of such rule. One of such rule to understand the quantum world. So when you make up a rule, you have to make some assumption, right? So
Yes, sir.
string theory says that every particle in the universe is made up of string, which are yes, they are made up of strings. And if different particles vibrate different way, you have a different
Hmm.
type of particle, right?
Yes, sir.
So
Yeah.
for you at the current stage, I would say string theory is simply a rule designed to understand quantum world. Okay.
Yes, sir, I understand. But once while I was going through a book written by Dr. Brian Greene, while I was
Mhm.
going through the Elegant Universe, I realized that even he mentioned in his own book only that I realized there is a problem where I'm not really aware of the exact values right now, but the mass of the string was becoming more than the mass of the actual particle that it was making. But how can
Okay.
something which is making up the product is having more mass? Is there something which is canceling the mass out in the process?
Okay, I won't comment on that. I'm not aware of that part, but I would say this. Of course, there is an issue with the string theory. For example, string theory says that you don't have a three dimension, but you have a
Yeah.
12 dimension or 8 dimension. All this
Hmm.
dimension other than three, we say extra dimension. So
Yes,
this
sir.
is the prediction of string theory. String theory says that you should have extra dimension. Now,
Hmm.
to test this theory, it is the job of again the LHC to test if really such dimensions there or not. Now, in those dimensions, there will be new particle. You'll see some new particle production. And in LHC, if we can detect those particles, then we can confirm whether extra dimension is there, which also confirm that string theory is right or wrong. As of now, there is no evidence of extra dimension in
Yes, sir.
any experiment. So we don't know how correct is string theory. So yes,
Hmm. Yes,
but
sir.
I would say I would not discourage anything. Why? Because if you know Higgs boson, and you know Higgs boson. Have you heard of it? Okay, so the person who says that there is a particle called Higgs boson in
Peter Higgs.
1960, yes,
Yeah,
he did it in 1964, I think, 1964,
yeah, that is.
and yes, and the particle was detected in 2012 or
Yes,
2012. Yes.
yes, sir.
Right.
Yes, sir.
Yeah, so
Hmm.
we don't know. Maybe sometime string theory can be correct, but as of now we don't have any evidence of string theory. So it's very much philosophical, and yeah, that's all.
Thank
I'm
you,
not
sir.
an expert on that.
Thank you. Yeah.
Thank you
So,
so much. Thank you for the question.
any other question? Okay. So, if not, let's thank Dr. Suman for wonderful talk. And I hope you all would have enjoyed a lot. I enjoyed a lot personally, and definitely you would have learned many things in this talk. So now I request everyone to please switch on their camera so we take a group photo. Everyone, please switch on your camera. Yeah. 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 Thank you all. So I have taken the screenshot. Screenshots. I will share in the website. Okay. So, Sanjay sir, you would like to add something at last?
Yeah, thank you, Suman sir, for nice talk. And I hope all the participants got benefited through this wonderful talk. I really enjoyed this talk. Thank you so much. Yeah.
Yeah, please, you can add your feedback using our website. So in context session, there is a feedback form in our website, aipbharat.org. Using that link, maybe I can post the link here in the chat box. So using that link, you can give your register your feedback. So you like it or not like it, or how we should improve, or any sort of comments or suggestions. All are welcome. So thank you all, and thank you, Dr. Suman, for joining us.
Thank you so much for this platform, and I really enjoyed giving a talk here, and the Q&A session was really tremendous, and I really enjoy that next generation people have really interesting questions to ask.
Yeah, it
in
was
the
really
group.
interesting actually. Yeah,
Thank you so
thank you.
much.
Thank you, Suman sir. Thank you.
Thank you,
Captain.
thank you,
Thank
thank
all.
you so much. Hmm. Uh, we'll have a meeting now, or
Yeah, we'll wait for 5 minutes. So then,
okay.
so our association core committee member can stay. Like Deepak is here, and
Yeah, Captain, you can stop the recording.